Hello everyone, welcome to the lecture 2 of EC 573 Advanced Embedded Logic Design Winter 2022 semester. This is the video 2 of the lecture 2. In the previous lecture, we discussed about the intelligent reconfigurable hardware software co-design. Now we will start our discussion on the bus protocol. So we are discussing the bus protocol, keeping the system on chip in mind. So what is bus? So bus is an important aspects of the SoC. As we know, SoC has all the functionality embedded in a system chip, but the bus becomes one of the most important aspects of the SoC. Bus allows different blocks of the SoC to communicate and share the data with each other. So it allows the processor to communicate with the memory. It allows the processor to communicate with the peripheral. It allows the peripheral to communicate with the memory and the different co-processors inside the system on chip. So in the bus infrastructure inside the SoC, there are two parts. One is the hardware part. Second is the software part. In the hardware part, you have the physical implementations such as cables, wires, which are used to connect the different blocks. While in the software part, it includes the bus protocol, which tells how the two blocks can communicate with each other, what are the protocols or rules on the regulation they need to follow. Okay, so the bus in a SoC can be a single bus for the entire SoC, or you can have the multiple bus. It all depends upon what is the user requirement, what are the delay constraint or the latency constraint, and what is the cost constraint of the user. Based upon that, you can decide the number of buses. Bus can be external bus where the SoC communicates with the other component, while it can be internal bus, which is the focus of the AELD, which is used to connect the internal component inside the system on chip. As we know, the internal bus has the less overlay, less capacitance, lower voltage, so it is much faster and it has the lower power consumption. Inside the system on chip, you can't have the cables or the metal traces. So your bus is nothing but the metal path integrated on a system chips. So in a bus, you can have the one master unit and then the one slave unit. Master is the one who initiates the transaction. What are the transaction? You transfer the data from master to slave, or you transfer the data from slave to master. So in the one you transfer the data from the master to slave, it is called as the write transaction. And when you transfer the data from the slave to master, it is called as a read transaction. So you may have the multiple slaves, so you need an address decoder to enable the appropriate slave. Similarly, when you receive the data, you need to choose which slave has been enabled, and appropriately that data you need to pass it to the master. So accordingly, you need to have the corresponding decoder and the multiplexer to enable the appropriate read and the write transaction. In general, you may see that the one bus which enables the read and write transaction consists of the three subparts. One is the data bus, which is used to communicate the actual data. But to communicate the actual data from one location to another, you need to have this additional handshake signal. For example, you need to provide the address. For example, you may have the multiple slave to which slave to be selected. Inside the slave also, you may have the multiple memory locations. So which location inside the slave you need to write to? For example, in the block RAM, or every slave may have the multiple registers. So you might be writing to the particular register. So you need to provide the address. And then you need to have the control signal, which says what kind of transfer it is, whether it's a burst transfer or the simple transfer, how many transactions are there in the burst, whether it is a lock kind of transfer. So additional different kind of control signal to communicate the information about the transaction and to successfully complete the transactions are present in the control signal. So control signal, address bus, and the data bus form a complete bus in a SoC. Sometimes you may combine the address bus and control bus together, and you can call it as a address and control bus. Okay, but the data bus is usually one. So why this is important? Why we are discussing the bus protocol? The first thing you can see is on the right hand side, you have the module A and then you have the module B. Module A wants to send the data to the module B. So you can see that there is a data bus. But what is the problem? The problem is, how does the module B knows that the data is valid? Because how does the module B knows at what time I should read the data? So what we can do, we can add the additional supporting signal, which is called as the valid signal, along with the data signal. And what does it mean? Whenever the module A sends the data, it will also raise the or assert the valid signal. When the valid signal is 1, then you can see that the data is valid. So module B knows that the when to accept the data. This is good. But then how the module A knows that the module, so how is the module A knows that the module B got the data, right? So how it knows? So what you need to do, you need to send some kind of acknowledgement signal. So you can add some kind of acknowledgement signal here. So maybe, okay, I have not shown it here, but maybe you can send that you can have some kind of acknowledgement signal here. Then it also we need to take care that the data bus from the module A to module B consists of the multiple 1-bit signal. There may be unequal skew between all the bits. So you need to make sure that this valid signal goes high when all these bits are stable to their appropriate value. So this valid signal need to be generated carefully. Okay. So this is the acknowledgement signal I was talking about, that the module A sends the data along with the valid, and the module B then sends the acknowledgement signal along with the corresponding valid signal to say to the module B that, okay, good, I have received the data and data is correct, or any other information. Now, the thing is, this looks good, but what happens when the acknowledgement from the module B is delayed? Should the module A wait for a long time and just keep on waiting for the module acknowledgement from the B, or module A can send the next set of data, or it can start the communication with another module? So that needs to be defined in the protocol. It should be carefully defined. Then you can see that how to use the bus more effectively. If you are keep on waiting the data, that means bus is not being used effectively. So one thing is that module A can send the next set of data before waiting for the acknowledgement. So you can see that the module is sending the X data, Y data, and Z data before waiting for the acknowledgement. So can a series of related or unrelated transfer have? How to manage this transfer? For that, we need a bus protocol. Then you need to see that can we have the overlapping transfer? For example, you can see that here you can see that the module is sending the Z data, and at the same time the module B is sending the acknowledgement for the A. So in this case, you can see that the module A is sending the data and also it needs to process the acknowledgement. Can this is supported in the bus protocol? That needs to be defined. Then you may have the burst transfer. You can see that there are multiple set of burst of data is being transmitted. So can the such burst transfer is supported? Also, you may have the out of order transfer. For example, here you can see that the data is sent in A, B, C in a particular order, but you can see that you are getting the acknowledgement from the B before you are getting the acknowledgement for it. Can is such things are supported in your bus protocol? That you need to understand. Then in the SoC, you have the multiple, you can have the multiple masters and multiple slaves, because everyone wants to communicate the data at a particular time. So who gets the access to the bus? You can't have the dedicated bus between each master and slave. So you need to decide who gets the access to the bus. So from the master slide, who gets the access to the bus? So you need to have some arbitration based upon some priority depending upon your system on chip or your user requirement. So whether this arbitration should be the centralized or decentralized, who decide this? Again, it will be defined in the bus protocol. Similarly, you have the multiple slaves communicated to the connected to the bus. So which particular transaction is there only for one particular slave? So how the slave knows that this is there for me? Whether the slave should keep on reading all the transaction going on the bus, or whether slave will get the appropriate enable signal by some centralized decoder unit. So whether the slave selection should be centralized or decentralized, this to be decided by the bus protocol. So that's why we need a bus protocol. And with the modern day SoC, heterogeneous SoC, your SoC consists of the large number of IPs or the blocks, and each of one is designed to perform the particular task. For example, your SoC may have the memory controller, it may have the UART, you have the USB, video controller, DSP processor, floating point unit, and so on, and SIC and FPGA accelerator. So you have each one is designed to perform the particular task. In order to talk with each other, obviously they need to talk with each other. Then you need to have the standard communication protocol, right? You can't have the different people speaking in their own languages, right? And when you come on the common platform, you need to speak in a one common language. Otherwise, the communication will not happen. So that's why we need a communication standard or protocol. But having just communication standard or the protocol is not sufficient. It needs to be flexible. For example, you may have the multiple units of the different communication requirement. You have the processor with the multiple cores which need to continuously access the instruction and data, and this to be run at the higher speed. Then you have the DMA which moves a large amount of data from peripheral to the memory, from memory to another memory. So it should be done as fast as possible. Then you have the video controller which sends the 2D data. So you need to send the data at a much higher frame rate. You have large amount of data. So then you have audio controller which can work at a lower speed. You need to support all this kind of heterogeneous requirements. So your communication standard should be flexible. It should be able to support all these requirements. There should be flexibility. Otherwise, it should not happen that I have to use one communication standard for one particular requirement, another standard for another requirement. This should not happen. So that's why there is a need of the flexible communication standard. To summarize, modern day design consists of large number of IPs. Each one is designed efficiently to perform the task. In order to talk with each other, we need a common communication standard which must be flexible enough. If this is not, there is no standard, then the handling of the incompatible IP interface, like for example, if you have a group, each one is speaking in their own native language, it's very difficult to communicate with each other or do some efficient work. So handling of the incompatible IP interfaces and assembling the heterogeneous IPs can take months. It is a very time-consuming task. So standard, when you have a communication standard, they define the specific data transfer protocol and they decide the number and functionality of the pins at the IP interface. So whenever you define the communication standard, it defines that, okay, this is your IP. It defines how the IP communicates with the outside world. It doesn't say anything about how your algorithm is implemented. It defines only the interface. So that means once you design the IP, which is compatible with a particular communication standard, you can sell it very easily. You can pass it to from your friend to any other your business partner very easily, because that another person needs to just understand how this IP interface works, and if he or she is familiar with that IP interface, he just need to communicate the data to the IP as an input and then receive the data from the IP output. He or she doesn't need to worry about how this IP perform the task. Only how to communicate with the IP is sufficient. Thus, availability of the such protocol makes the maintenance easy. You can maintain the IP very easily. When you go from the one version to another version, you know that the protocol communication standard is the common. So its maintenance understanding is very easy from one team member to another team member. Debugging is easy. If something is wrong, you know that how to debug your IP. You can reuse your IP. For example, If you are going to go starting a new project and you want to use something from the old project, you can use the IP as it is, because you know that the interface remains the same. You don't need to redesign the IP. Similarly, when you are going from lab 1 to lab 2, if you are working on the different protocol in each lab, that becomes very challenging. But if you are using the same protocol throughout the lab, you can use the modules which are developed in the lab 1 in the lab 2 and so on. And the future upgradation also easy, because if you want to your team, suppose that the new team comes, your old team leaves and the new teams comes, they can start on the working on your IP and add the new features in the algorithm without changing anything in the IP interface. So you can modify anything inside the algorithm, you can upgrade anything inside the algorithm without worry about the compatibility or the communication with the other. So that's why there is a lot of work is done on the developing the communication standard, and now there is a requirement of the flexible communication standard. So over the year, there were multiple communication standards are developed. AMBA is the one, Core Connect from IBM, Wishbone from the Open Course, and the Avalanche from the Altera. So each has their own requirement, each has their own features. And in our AELD course, we are going to study about the AMBA protocol. Okay. Why we are studying on the AMBA protocol? The first thing is it is one of the popular protocol available in the market. Second, it is free, open to use. Third, the hardware which we are using, that hardware is also based upon the AMBA protocol. So if you want to design something, we need to understand the AMBA protocol. But again, the focus is on how to understand one particular protocol, right? That is very important. If tomorrow, if you want to move from the AMBA to Core Connect, you should know how to learn some protocol. What are the basic challenges are there, or what are the basic issues are there which are addressed in the protocol. So that's very easy to move from one protocol to another, as long as you understand why the protocols were developed and what are the particular issues which are there between the communication between the different IPs in the SoC. Okay. So in the next video, we will discuss more about the AMBA protocol.